Hi, hello, namaskara. Myself Mahesh Prasad, as you know, from Department of Physics. So we already started up with the chapter called as Mechanical Properties of Solid, right? So we have covered n number of topics like stress, strain, and based on this concept of stress as well as strain, we have got different types of modulus elasticity like Young's modulus, bulk modulus, shearing modulus, right? So by taking the help of this particular concept, so today we will discuss one of the topic called as Poisson's ratio. Okay, so which ratio? Poisson's ratio. So obviously, before we get into this, I'll give one example. So there is a rubber band in my hand, and it is having. Don't you think this rubber band which is having some diameter initially? For example, if the diameter which is having a initial diameter as 1 mm, 1 millimeter, and if I stretch somewhat like this, do you think the diameter is increases or decreases? So obviously, when I stretch or when I apply a stress, what happens? The increase in length will take place. At the meantime, the diameter of the object or this rubber band is going to decrease. Correct? So before we get into this Poisson's ratio, we need to know one more definition that is called as lateral strain. That is the lateral strain. The lateral strain, which is nothing but which is a change in diameter to the original diameter. So which is nothing but change in diameter to the original diameter. So what is the change in diameter we can have over here? The change in diameter, whether the diameter is increase in diameter or decrease in diameter when we stretch. So obviously there will be a decrease in diameter will take place. So that I can have minus delta D divided by so nothing but we have, what is the change in diameter we have? That is the delta D divided by, what is the original diameter I can have? That is the D, which is equal to lateral strain over here. So what do you mean by minus over here? Minus sign which indicates what? Decrease in diameter or decrease in dimension. So delta D is a change in diameter or decrease in diameter. So D was the initial diameter. Okay. Next one is, as you know, one more is the longitudinal strain. What do you mean by longitudinal strain? We have that is a change in length to the original length we have. Correct? Now, what is the change in length we have? That is nothing but delta L. What is the original length we have? That is L. That is equal to longitudinal strain over here. Now, your job is to get the Poisson's ratio. The Poisson's ratio, which is nothing but it is a ratio of lateral strain with respect to the longitudinal strain. So, which means that the Poisson's ratio is denoted by sigma. So sigma is equal to what I can have over here, that is the ratio of lateral, that is the lateral strain divided by longitudinal strain. Longitudinal strain over here. Okay. So what do you mean by lateral strain I can have over here? What we got over here? That is nothing but minus delta D divided by what is the longitudinal strain we have? That is delta L divided by L over here. So this is equal to S. So this is the formula I can have for Poisson's ratio. So what is by Poisson's ratio? Which is nothing but it is a fractional change or it is a ratio of lateral strain with respect to longitudinal strain. What do you mean by lateral strain, by the way? Which is nothing but decrease in diameter with respect to the original diameter. Why it is decrease in diameter? Because you have applied a force somewhat like this. So what happens? Decrease in diameter will take place. Diameter of this particular wire is going to decrease. So this is how exactly it works. And one more compressibility, that is somewhat like this. That is compressibility. So compressibility, which is nothing but it is just like inverse of bulk modulus. What do you mean by bulk modulus, by the way? Bulk modulus, which is here compressibility, which represents K. As you know, it is inverse of bulk modulus. What do you mean by bulk modulus? It is the ratio of bulk stress to the bulk strain. So this is how exactly it works. And the bulk modulus, we have achieved a condition F by A divided by delta V by V. That is nothing but, so here I can write it as delta V by V divided by F by A. So this is how exactly it works. Okay. So whenever they ask to find a compressibility, if you initially supposed to get the bulk modulus, then you do the inverse of that value. So you are going to get, this is a capital K. Capital letter K gives a compressibility. So what we all have studied, that is the Poisson's ratio. What is the Poisson's ratio? It is a fractional change in, or it is a ratio of lateral strain with respect to longitudinal strain. Longitudinal in the sense what? We are stretching something by applying a force. So this is what exactly we can expect under the concept of Poisson's ratio by denoting sigma. And here one more term, that is compressibility. Okay. So yeah. Yes. Well, dear students, we'll move on to the one more expression. We'll try to get, or we'll try to achieve that particular condition which is there on the board. That is expression for elastic potential energy per unit volume. So we'll try to achieve this particular derivation. Okay? So what do you mean by potential energy? Energy is stored in terms of its position, right? So there is one wire somewhat like this. Okay, there is one wire. For a time being, I am not applying any force. So which is at rest, which is having some length as yellow. Okay. Now, at this particular moment, do you think any force which is applied over here? No. So initial force is 0. So I can have the initial force, if I take it as 0, then what is the final force? After applying the some force, I can have an increasing length. For example, I can have delta L over here, which is nothing but direction of force, which is downward direction. So which means I have applied some force so that there is an increase in length will take place. Correct? Now, how to take average force? So average force which is equal to, I can have 0 plus F divided by 2. Correct? Now initially I have not applied any force, that is 0. Then after applying the force, that is F. How to take average? Divided by 2. So average force which is equal to, I can have, that is F by 2 over here. Correct? Now what do you think, if I want to stretch from one point to another point, I need to do some work. Correct? For example, I am standing over here. I want to go from one point to another point. I need to do some amount of work. Somewhat, if I want to move from one position to another position, right? Now, so similarly, what is the amount of work done by stretching a wire? So what is the amount of work I need to do to stretch a wire from one point to another point? So what is the formula we have for work done? That is a force into displacement. That is a work done, it is equal to force into displacement. What is the displacement we have over here? That is the delta L. What is the force? That is the average force. So the amount of work done, that is the amount of work done by stretching the wire, I can have, that is U, which is equal to, U is the potential energy or amount of work done, which is equal to, that is force average or average force into increase in length, that is increase in length I can have what I can have over here, which is equal to what is the place force we have, that is F by 2, that is F by 2 into delta L, which is equal to U, or else let U, which is equal to half into F into delta L, and this is the energy stored, or this is the amount of work done by stretching the wire from one point to another point. That is one point. Now we need what? We need what? That is a potential energy per unit volume. So if I want to get a potential energy per unit volume, what is the volume of this wire I can take over here? That is area into length. So we have, that is the volume of the wire, which is equal to, that is the area into the length of the wire. Now if I want to get, that is the elastic potential energy per unit volume, if I want to get, so what I suppose to do, U divided by, that is small u, is equal to U divided by V, correct? So what is the potential energy we got? That is half into F into delta L divided by, what is the volume we have? Area into length. That is area into length. So altogether, what I can write over here? That is U, which is equal to, that is a half into, that is F by A into delta L by L over here. Now F by A is nothing but a stress. Delta L by L is nothing but a strain. So it is equal to U, which is equal to half into stress into strain. Now, do you think if I do stress, so if I do for this case strain by strain, will it affect actual value over here? No, right? If I apply 2 by 2, nothing but 1 into anything is anything. What is anything? I can have this much, correct? So now, U, which is equal to, if I multiply this strain over here, stress by strain, which is nothing but longitudinal stress by longitudinal strain, which is equal to what? That is Young's modulus, right? Correct, no? Longitudinal strain divided by longitudinal stress by strain, which is equal to Young's modulus. So this is also can be taken as Young's modulus into strain whole square. That is the strain whole square. And this is also one more condition I can have to get the answer over here. So this is one point of it. So there are a number of things which may come to your mind. So this is how exactly it works. That is the expression for elastic potential energy. And here also we can have application of elastic behavior. There are a number of applications we can find. This is the first one we can have to find maximum height of a mountain, as well as we can by selecting the rope of the crane, by selecting rope of the crane. So this is the basic things, because see, to find the maximum height of the mountain, if we know the value of pressure, which is equal to rho GH, so if you know the value of pressure which is exerted on the base as well as the density of the material, and G obviously you know, so directly you can go with the height value. So by using this, we can have the maximum height 10 to the power 4 meter. If you substitute the value of pressure as well as density, that is pressure we can take 3 into 10 to the power 8, as well as density we can take 3 into 10 to the power 3 we can take. So if you take so I think so, yeah. So 8 as well as 6, so that you are going to get height as around this much. And you know what is the maximum height of the mountain right now in the world? That is Mount Everest, which is around 10 kilometer, right? So obviously which is less than this. So based on the properties of the material, or based on the elastic property of the material, we will get to know how much height it can take. So if it crosses this particular height, so by of its own weight it is going to collapse. Are you getting? So that's why we can use its elastic behavior as well. Okay? Yeah. Because pressure you can take it as 3 into 10 to the power 8 Newton per meter square, as well as the density you can take 3 into 10 to the power 3, that is kg per meter cube. So if you substitute this value, you are going to get around this much. And also by selecting the rope of the crane, so which means by taking the Young's modulus, we can take, normally we used to have a steel wire in the crane. Why? Because if I compare the steel wire with respect to aluminium wire, the steel wire is having a greater Young's modulus, which means it requires greater force to elongate, to get a delta L, to get a more strain. So that's why a steel which is comparatively better choice than aluminium wire, so that you can lift any object easily. Okay. So this is how exactly it works. There is application of elastic behavior of the material. Okay. Yeah. Well, based on our concept which we discussed so far, we will discuss one numerical so that you will get a better idea about a particular scenario. So there is one question which you can see on the board, that is when a rubber ball which is taken into a depth, there is a rubber ball which is taken into the depth of 100 meters. So what happens? Where in the sea, its volume which is going to decrease by 0.1% of initial volume. So if the density of the sea water is 1000 kg per meter cube, then calculate the bulk modulus. So what is the bulk modulus we have over here? The formula, bulk modulus which is equal to, that is F by A divided by what we have, that is delta L divided by A. Since it is the pressure will comes into the picture, this can be written as pressure divided by delta V divided by V. Correct? Now we are job is to get the initially what is the delta V I can have, that is the delta V that is equal to, that is 0.1% of original volume, that is the original volume. Correct? So which is equal to, that is a 0.1 into V divided by 100, which is equal to delta V. And what about the pressure? I can have pressure which is equal to P, which is equal to rho GH. And remember this formula, and if you get a derivation in the next chapter. For time being, you remember this formula. Pressure which is equal to rho is the density of the water, G is acceleration due to gravity, H means at what height your object which is located. Okay. So density of the water is 10 to the power 3 into 9.8 into height is 100, because height is given as 100 over here. Rho is the density of the water, which is nothing but 1000 over here. Now what is the pressure? I can have pressure which is equal to, that is 9.8 into 10 to the power. So altogether we can have pressure which is equal to 10 to the power 5 I can have. Correct? 10 to the power 5. Pressure equal to Newton per meter square. So how do you apply your bulk modulus over here? Bulk modulus which is equal to pressure divided by delta V by V, which is equal to, that is 9.8 into 10 to the power 5 divided by 0.1 into V divided by 100 into V. V will get cancelled. So what is remaining over here? That is bulk modulus we can have, that is 9.8 into 10 to the power 8 Newton per meter square. And one more thing you are supposed to get, that is the compressibility. That we know compressibility which is nothing but it is the inverse of bulk modulus, right? So now compressibility K is equal to 1 by, that is 1 by bulk modulus, which is equal to, that is 1 by 9.8 into 10 to the power 8, which is equal to, that is 0.102 into 10 to the power minus 8. And what should the unit I can have inverse of this? That is Newton per Newton with square. And this is how exactly we can have compressibility equations. Okay. So initially we got the bulk modulus when a rubber bar which is moved towards earth, moves towards sea water with a height of 100 meter. So this is the height, the object is located depth of 100 meter, and we know the density of the water, that is 1000 kg per meter cube, that substituted over here. Then and delta V, which is nothing but change in volume, which is nothing but 0.1% of original volume. So since it is the percentage divided by 100, so into V, because with respect to initial volume which is decreased over there, then we got a formula like bulk modulus which is equal to pressure divided by delta V by V, and we got this much, and inverse of bulk modulus we got compressibility. So this is how exactly it works. Yeah. Thank you very much. Okay.